So today we're going to continue with our notes. So you'll need to get out your notes packet and look where we stopped. So we're going to continue learning about finding max and mins of functions without a calculator. So we stopped right before this example, but I want you to try f of x is equal to x cubed minus 12x on 0, 4 by yourselves, and then I'll put the answers at the end of this video for you to check. But I want to do this one because it's a little bit different. So if you read through the notes that we went through last time, a big caution is that you need to check the domain of a function, and this is where it comes into play. So if I rewrite this function, I get 6 the square root of x cubed minus 4 the square root of x. And if you remember, you can't have a negative in a square root. So this domain actually starts at 0 and goes to infinity. So if you have a square root function, a rational function, or a log function, you need to check the domain and write that out first, especially if they don't give you a domain. Now we're going to do the first derivative test to find the local max mins, global max min, and where the function is increasing, decreasing. So I take the derivative. So we get 9x to the 1/2 minus 2x to the negative 1/2. And I'm going to rewrite this because I'm going to need it simplified in order to solve it. So to find the critical points, we set the function equal to 0, and we need to find where the derivative is 0 or undefined. In order to do that, you have to get a common denominator. So I'm going to multiply 9 the square root of x by the square root of x over square root of x. And that gives us 9x minus 2 over the square root of x. And to find the critical points, we're going to set the numerator equal to 0 because that makes this function 0. And I'm also going to set the denominator equal to 0 because that's where it is undefined. So we get x equals 0 and x equals 2/9. And so those are my two critical points. I'm going to put them on my number line for my sign chart, and 0 is an endpoint because that's where it starts. If you forgot to do this, you would try to plug like negative numbers into your derivative, and you would get that that number doesn't exist because you would take the square root of a negative. That would be a hint to go back and check your domain if you get an unreal number for your derivative. So I'm going to try things in each interval. I'm going to try like 1/9. I'm going to plug it into the factored form because it's easiest, especially without a calculator. So if I plug it in here, 9 times 1/9 is 1, and then 1 minus 2 is a negative 1, and then negative 1 over the square root of 1/9. No matter what, it's going to give me a negative number. All we care about is the signs again. So this part is decreasing. Then I'm going to try an easy value like 1 probably. If I plug 1 into here, 9 minus 2 is 7 over 1. That's a positive number. And so this is increasing. This is my 0. So this is a min because my function is increasing, decreasing. 0 is a max because my function started up and then it's decreasing. I need to find the y values in order to figure out what the global max or min is. In this case, though, we only have one min, so the global local min has to be at 2/9, and then I still need to find the y-coordinate, and then the local max is at 0 something. I'm going to go back and find the y-coordinates, but there is no global max because this increases forever to infinity. So I'm going to plug in 2/9 to my original function, and you can use your calculator for this to find it, just to save time. So plug that in to see what you get. And if you do that, you get negative 1.257. I'm going to make it accurate to 3 decimal places. And then the local max, if I plug 0 into here, I get 0. And then again, absolute max, there is none because this function is going up forever to infinity. So that's just an example of when it's undefined and you have to find where the denominator is 0 as well. So I want you to try this one. When you do the trig functions, you're going to have to factor out a trig function of the derivative and then set each one equal to 0, and I'll put the answers again at the end. So today we're going to learn about the second derivative. So the second derivative tells us the concavity of the graph. Just remember, concavity is how the graph's turned. So this is concave down, and this is concave up. When the second derivative is positive, the graph is going to be concave up, and when the second derivative is negative, the graph is concave down. So the reason is that the second derivative is the derivative of the derivative, so it's looking at what is the slope of the derivative doing. So for this, and a concave up function, if you draw your little tangent lines, this slope is really negative, and then it's getting less negative, and it's getting more positive. So the slope, the values of the slope are increasing, which means the second derivative is positive because the slope of the derivative is increasing, and that makes the second derivative positive. The function is concave up. When you're concave down, you're starting with like a really steep positive slope. It's going to 0, and then it's getting more and more negative. So this slope is getting smaller, which means that the first derivative is getting smaller. So if you took the derivative of that, the second derivative ends up being negative for concave down. We'll do a lot more with this concept, and I'll explain it again in class to hopefully help, but it can be somewhat confusing when you're thinking about how the second derivative relates to the original function. So you might just want to memorize this principle as well. If the second derivative is positive, my graph is concave up. If it's negative, my graph is concave down. For f of x, if f of x is concave up, we said this before, f prime is increasing. And if f of x is concave down, f prime is decreasing, which means if the second derivative is negative, because we said if the second derivative is negative, then my function is concave down. That means that f prime is also decreasing. And if f double prime is positive, that means the original function is concave up, f prime is increasing. So when we're looking at the second derivative, we're looking at like what's happening with the steepness of the slope, or what's happening with the values for the slope. Are they getting bigger or smaller? A point of inflection occurs where the graph changes concavity, and f double prime will either be 0 or undefined, which again means that we're going to get 0 in the denominator. For the graph to change concavity, f double prime must change sign. Okay. So it must change from concave up or concave down, which means the second derivative has to change sign. This is just an important part. If the second derivative is 0 or undefined, the second derivative must change sign for that point to be a point of inflection. If the second derivative does not change sign, the point is not a point of inflection. If you look on page 213 in your book, they show this and explain it in more detail. So if y double prime is 0 at a point of inflection, y prime will have a maximum or a minimum. And we use the second derivative, not the second derivative test, to determine concavity. We'll get into the difference between them in a second. To find the concavity, we make a sign chart for the second derivative to figure out when a function is concave up or concave down. So on page 213, and you can look this up in your book, there's two important things they tell you to caution. So the first one, I wrote it here, is the second derivative can be 0 at a non-inflection point. So if we take the first derivative of this, we get 4x cubed. The second derivative, we get 12x squared. I'm going to draw a sign chart for the second derivative. So if we do that, we put where the second derivative is equal to 0, and if you solve this, you get x is equal to 0. And you do the same thing we did for the sign chart for the first derivative. You try values to the left and right, but you're going to plug them into your second derivative. So if I plug -1 here, I get a positive 1, which this should say positive 1. You get a positive. This was 0. So my function, what we put, if it's the second derivative, we put concave up or concave down. So I'm going to put a u up. So this is not a point of inflection even though the second derivative is 0 because it stays concave up. And if you graph this x to the fourth, looks like x squared is just levels off more at the bottom. So the whole time it's still concave up even though the second derivative is 0. For the second one, the second caution, the second derivative need not to be 0 at an inflection point. It may be undefined. So again, if I take the derivative of this, I get 1/3 x. If I subtract this to the -2/3, if I take the second derivative, I get -2/9 x. If I subtract 1, I get to the -5/3. So we're going to check where this is 0 or undefined. So if I rewrite this, it's -2/9 and then it's the cube root of x to the fifth. If I'm going to figure out where this equals 0, it never equals 0, but the denominator does equal 0. If I solve this, I get the cube root of x to the fifth is equal to 0, and that would be x is 0. And so if I make my sign chart again, at 0, I'm going to put UND or infinity because it's undefined. Before 0, if I try f double prime of -1, the cube root of -1 to the fifth is still negative, so I get a negative over negative, so this is positive, and my original function is concave up. If I try 1, I'm going to get a negative over a positive, so this is negative and this is concave down. And so this is a point of inflection because the second derivative changes sign. And in this case, the second derivative is undefined. So the second derivative, if it's undefined or 0 and the second derivative changes sign at that point, then it is a point of inflection. So the second derivative test can be used to find max and mins. These are the steps for it. You find the critical points using the first derivative. You find the second derivative. You plug the critical points into the second derivative. If the second derivative is positive, then f is concave up and the critical point is a, so if I draw it, if I have a concave up and at a critical point it's going to be the lowest or the highest point because that's where the derivative is 0. If you have concave up, it's going to be the lowest point, so this point is a min. If the second derivative is negative, then the function is concave down, and that makes the critical point a max. You can always draw a picture of a concave up and concave down function to determine if it would be the max or the min for the critical point. If the second derivative test is inconclusive, if the second derivative is 0 or undefined at a critical point, you must then do the first derivative test, determine if the critical point is a max, min, plateau point, or vertical tangent. Same with endpoints. You may only use the first derivative test to determine if endpoints are max or mins. So sometimes you're going to have to justify for the second derivative test, and these are the 4 things you must include in your justification. That you're looking at a critical point, or f prime is 0 or undefined, the sign of the second derivative at the point, the concavity of the original function, and that the point is a max or a min. So we're going to do a few examples. So the first example It says use the second derivative test to find the max and min. So I'm going to follow the steps we just said. I'm going to take the first derivative to find the critical points. I'm going to use chain rule. Don't forget to multiply by -1. And I'm going to set that equal to 0. So to set that equal to 0, I have -2, 2 minus x is equal to 0. I can divide by -2 and I just get 2 minus x is equal to 0, and then x is equal to 0. So this is my critical point. Then we take the second derivative. So to take the second derivative, I'm going to rewrite the first derivative by distributing the -2 just to make it easier. And then if I take the second derivative, no matter what, I get a +2. And sorry, my critical point isn't 0. My critical point over here is 2. Because if you do 2 minus x and you add x, you get 2. So back to my second derivative. It's always 2. If I plug in 2, I'm still going to get out 2. So what that means is at 2, my function is concave up. And then since it's the critical point, it's where the derivative is 0, which makes that a min. So you don't have to justify it for this one, but I'm going to write the justification just so you can see. So to justify this, you would say x equals 2 is a min because, and you have to include these 4 things. Either f prime of 2 is equal to 0, or you can say x equals 2 is a critical point, and f double prime of 2 is negative, and you also have to say f of x is concave up at x equals 2. So you must say all 4 things. X equals 2 is a min because f of 2 equals 0, f prime of 2 is negative, I don't need that and f of x is concave up at x equals 2. So you have to include those 4 things when you justify it. So that is the second derivative test. That helps us find max and mins. We use just the second derivative to determine the concavity of the function by making a sign chart like we do for the first derivative. So I'm going to do f and f double prime. I'm going to use what we just said. So my critical point is 2. But there are no points of inflection because it's always 0. So you don't have to put a 2 here actually. You can just, there are no points of inflection. So we just always have my second derivative being positive, which means my function is always concave up. So I would say concave up from -infinity to infinity. And the only reason it's always is because there's no values where the concavity changes. There's no values where the second derivative is 0 or undefined. Okay, so the second example, find the critical points of x to the fifth minus 5x to the 4 using the second derivative test and justify your answer. So you might want to pause and try this first before you watch it to make sure you understand it. But if you try this, we first, again, take the first derivative. So I get 5x to the 4th minus 20x cubed, and I set it equal to 0 to get my critical points. So I'm going to factor out a 5x cubed, and I get x minus 4. And then x is 0 and x is 4. Those are my 2 critical points. I'm going to take the second derivative from this function, which is 20x cubed minus 60x squared, and then I'm going to plug my 2 critical points in. So if I plug in 0, I get 0, and if I plug in 4, again, all you care is if you get a positive number or a negative number. Again, if you want to use your calculator just for this part, you can, but if you do this, you get 10,040. So this is a positive. Now, we can tell x equals 4. So if we were doing this, x equals 4 is a min again because f prime of 4 is 0. f double prime of 4 is positive, which makes f of x concave up at x equals 4. Okay. So that would be my justification. The problem one is the 0. So when you get 0, we said a few slides before, is that the second derivative test is inconclusive. So for 0, what you would have to do is you have to go back to the first derivative test and make a sign chart. So I'm just going to write it over here. So to do 0, I'm going to, again, go back to my first derivative test, make a sign chart. So I get my critical point is 0. I'm going to plug in like -1 into my first derivative, which is up here again. If I plug in a -1, I'm going to get a negative times a negative, so that's a positive, so that's increasing. If I try f prime of +1, you can try anything, just don't go bigger than 4 because that's your other critical point, so it won't give you the right answer. If I plug it into my factored form, I get 5 times -3, so that's a negative, and that shows you that x equals 0 is a max. To justify with the first derivative test, you have to state that, again, so x equals 0 is a max because, so for this you need to include that, again, the derivative of that point is equal to 0 or undefined, and f prime of x changes from positive to negative at this point. Okay, so that's how you justify a first derivative test. You're on to. So that gives me the max and mins, and the only reason we had to go back and do the first derivative test is because the second derivative gave me 0, so it's inconclusive. Then to determine where the function is concave up or concave down, I'm going to do a sign chart with my second derivative again. I'm going to put my two values where the second derivative is 0, which I didn't find yet. So come back up here. I'm going to set my second derivative, so 20x cubed minus 60x squared equal to 0. I'm going to factor out a 20x squared, and that gives me x minus 3 is equal to 0. So my two critical values where the second derivative is 0 and 3. So that's what I put on my number line for the second derivative, where the second derivative is 0. And then I'm going to do values in each interval. So I'm going to do f prime of -1, 1, and like 4. So we already found f prime of 4 up here. It was positive, so that's increasing. If I try -1 and I plug it into my second derivative, this gives me a -20. This gives me a -60, so I get a negative minus a negative, so that's negative. If I try 1, I get 20 minus 60, so that's also negative. So here I have concave down, because the second derivative is negative, concave down and concave up. So 3 is my only point of inflection, because that's the only place it changes sign. So then if I'm writing concave up, I would say it's from 3 to infinity. Down, I'm going to say from negative infinity to 0 and 0 to 3. I'm not including 0 because the second derivative is 0, so it doesn't have a point of inflection, or it doesn't have concavity at that point since the second derivative is 0. Okay, so that's another example of how you find it when the concavity changes. And so what that makes, just so we know, a point of inflection would be at x equals 3 only. So then the last example, find the max and mins of f of x equals x squared minus 3 times e to the x using the second derivative test. So I'm going to take the derivative. I have to use product rule, so I'm going to do first Derivative of e is itself plus the derivative of the second, which is 2x times e to the x. I'm going to set that equal to 0. Always factor if you can. So I'm going to factor out e to the x, and then I get x squared plus 2x minus 3. Factor that, so I get x plus 3, x minus 1, and then I'm going to set each term equal to 0. So I get x equals negative 3, x equals 1, and then this, you can either realize that e to the x looks like this, so it's never 0, or if you take the ln of both sides, you get x is equal to the ln of 0, which doesn't exist, so this one is canceled out. It doesn't work. So my only two critical points are negative 3 and 1. So then I'm going to take the second derivative. It's kind of messy because you have to do product rule twice with this. Or you could use your factored out term. That might be a little bit easier, actually. But either one, it doesn't matter. So I'm going to take the derivative of e to the x times x squared plus 2x minus 3, because then I only have to do one product rule. But you could do up here, you would just have to do two product rules. So I'm going to do first, the derivative second is 2x plus 2 plus the second times derivative of e, which is itself, and I'm going to plug in negative 3 and 1. What I recommend doing is factoring out your e to the x. So then I get 2x plus 2 plus x squared plus 2x minus 3. And combining your like terms before you plug it in, it might just make it a little bit easier. So I'm going to get x squared plus 4x minus 1. So now I'm going to plug in my two values. I'm going to plug in negative 3 and 1, and I'm just trying to figure out the signs. So e to the negative 3, and then I get negative 3 squared plus 4 times negative 3 minus 1. What you have to remember is e is always positive. So this really doesn't matter because it's always positive. So I get 9 minus 12 minus 1, which is going to give me a negative number. And if I plug in 1, again, this is positive, but I get 1 squared plus 4 minus 1, so that gives me a positive number. So what this means is that x equals negative 3. My function is concave down, so x equals negative 3 is a max because f of x is concave, and the order you say it doesn't matter, concave down, and f double prime of x is negative at x equals negative 3. And you just have to also make sure you state that f prime of negative 3 is equal to 0, or it's a critical point. Or else, because if you pick another point on this that's not a critical point, that's not a max or min. So it's very important that it's a critical point, or the first derivative is 0. And then for x equals 1, my function was concave up, so that makes it a min. So x equals 1 is a min. Kind of the same reason, because f of x is concave up, since we know that because f double prime of x is positive. At x equals 3, you need to specify the value, or sorry, not 3, 1. And you could also say x equals 1 is a critical point. So if you want to say that instead of f prime of 1 is equal to 0, that's fine. Okay. So that's the last example. Go back to the first ones, and I'm going to fill in the answers. So go back to these two examples. If you haven't done, like, pause and then come back to see what those two answers are. So here's the answer to the first one, so you can pause the video to watch it. If there's only one min, I just tend to put like global, local in the same line to save room, but you can see the sign chart and then all the answers, and you can check it. And then when you're done checking that one, you can come to this problem and I'll write the answer in and then you can check it again. So here's the answer for the last one. So you take the derivative, don't forget chain rule on sign. When you do a trig function, you factor out what's in common, set each one equal to 0, solve for the trig function, and then you have to figure out when is sine 0, and that's at 0 and pi. When is cosine a positive 1/2? That's only at pi over 3 on this interval. Make your number line, plug in, like pi over 6 is the only unit circle value I did. I plugged in it, and cosine of pi over 3 is square root of 3 over 2, so the 2's cancel. And I know the square root of 3 is bigger than 1, so this is positive. If I plug in pi over 2, because that's the easiest because you get 0 for cosine, you just get negative 1 times 1, so that's negative 1. And then you plug your 3 values into your original function to get the y values. And then this is what you get for min, max, increasing, and decreasing. So you can check your answers on that as well. So your homework, other than watching this video, is to also do the 8.1a front and back on the number line graphs and the 8.2a max, min, and points of inflection, just the front of that second page.